Good morning, good afternoon, or good evening. I'm Cam, and welcome back to Quick IB Chem with Cam. Today we're going to be covering topic R1 for IB Chemistry, SL, and HL as a review. R1 is going to have the following subtopics: R1.1, R1.2, R1.3, and R1.4, which is going to be its own HL topic. So if you're SL, don't you worry too much about entropy and spontaneity when that comes up. And you might notice that this video has already been published already, but I wanted to re-record it because I believe that that video was rushed and that you guys deserve something better. So without further ado, the first thing that we're going to talk about is energy, temperature, and enthalpy. So in chemical reactions, energy is needed to break bonds and is released when new bonds are formed. And that's going to kind of form the basis of the rest of this chapter, as you're going to see. Temperature is the measure of the average kinetic energy of particles in a system and is independent of the amount of substance. You're going to have to know this definition for your exam, so make sure that you memorize that temperature is the measure of the average kinetic energy of particles, right? Now, next thing we're going to talk about is heat. Heat is actually going to be different from temperature because heat is the total energy transferred because of a difference in temperature. Now, heat, unlike temperature, does depend on the amount of substance. Now, most of the time, you're going to see, unlike temperature, you're probably not going to have to define heat, but you will have to understand how you use heat and the chemical equation P equals mc delta T, which is going to be measured in joules, right? So C is going to equal specific heat. Heat is the specific heat, which is the heat needed to change the temperature of 1 gram of a particle by 1 Kelvin, right? So Q is going to be equal to your heat, M is going to be your mass, C is going to be your specific heat, and delta T is going to be your change in temperature. Now, the big thing that we're going to have to understand is enthalpy, A, or otherwise represented by H, which is the measure of the total energy in kilojoules per mole stored in a system. Now, your enthalpy can either be given by the enthalpy of your products minus the enthalpy of your reactants for a chemical equation, or it can be given by Q divided by mole, right? And so here you can see how if temperature is kinetic energy and heat is the difference in temperature and enthalpy is the total energy, then that's how you can see how enthalpy is related to heat. And do notice that on your exam, if you ever do have to calculate enthalpy from heat, you always want to make sure to divide your Q by 1,000 because this is in joules. You need your answer in kilojoules per mole. Lastly, you're going to need to know that thermochemistry is the study of energy change. Calorimetry is the method used to measure heat transfer. Now, second, we're going to look at what calorimetry looks like. Now, don't worry about most of the equations that you see in this, or all the equations actually that you see on this slide, because they're all in your data book. So don't feel pressured to memorize any of them. Now, here we can see a chart for exothermic and endothermic reactions. Now, exothermic reactions occur when energy is lost from the reactants or the overall system. And so your exothermic reactions are going to be hot, right? So if you look here, you can have potential energy on the y-graph, the y-axis, pardon me, and the reaction progress on the x-axis. So we can see that the reactants have a higher potential energy here. And to react in the chemical equation, they're going to have an activation energy, which is going to be this little hump. And then after that activation energy is reached, the chemical reaction is going to undergo. And because it's an exothermic process, you're going to go all the way down here until your products are at this potential energy, or this energy, right? So the distance or the difference between your products and your reactants is going to be your delta H, or the energy release. Now, because it's going to be H of products minus H of reactants, you can see how delta H is going to be negative. Similar thing in the endothermic process. You're going to have reactants that have low potential energy, and you're going to have to put a lot of activation energy in to make the chemical reaction actually, happen. And that's going to cause a spike in energy, and you're going to end up with products that have more energy total in that system. Your endothermic processes are going to feel cold. So if you're ever asked to describe them, or if there's ever a description like that, just know exothermic is hot, endothermic is cold. Now, delta H theta is just the standard enthalpy change of a reaction. Now, this is standard enthalpy change at a temperature of typically 900 or 298 Kelvin, and a pressure of 100 kilopascals, with solution concentrations of 1 mole per cubic decimeter. Now here's an example of calorimetry that we were talking about earlier. You're going to have your system, or your chemicals, dissolved in water. You're going to have often going to be done in a styrofoam cup. You're going to have a thermometer to measure the change in temperature as the reaction goes. And typically, to get your activation energy, you're going to have kind of like a burner under the cup to supply heat to the reaction. Of course, not directly on the styrofoam cup, fire. But styrofoam cups are effective for calorimetry because it has a low specific heat, making it a good insulator, and so basically saying it conducts heat well. So you're able to hold your system in the cup, and you're able to heat it up, and that heat's going to transfer from the cup to the system very effectively. Now, in calorimetry, if it's ever asking you why experimental values may be different from theoreticals, you want to say that there will always be a heat loss to surroundings, right? Because you can't ensure that all the energy from whatever burner or source you're using is actually going to go into that cup and into the system. Because some heat's going to go this way, some heat's going to go that way. So, in the metaphorical burner right here. And then, unless specified otherwise, always assume that your specific heat is going to be of water. Now here's an example of calorimetry. 50 centimeters cubed of 1.0 mole per cubic decimeter hydrochloric acid solution was added to 50 centimeters cubed of 1.0 mole per cubic decimeter sodium hydroxide solution in a polystyrene beaker, which is basically just another form of styrofoam. The initial temperature of both solutions was 16.7 degrees Celsius. After stirring and accounting for heat loss, the highest temperature reached was 23.5 degrees Celsius. Calculate the enthalpy change of this reaction. So first thing that you're going to want to do is you're going to want to write the equation, right? So if you're going to have hydrochloric acid and sodium hydroxide, you're going to have hydrochloric acid aqueous, because we know it's a solution, plus sodium hydroxide aqueous, it's a solution, to make sodium chloride and water. So you have an acid, and you have your sodium hydroxide, which is going to be a base, and your acids and your bases mixed together to get a salt and water. Now, the second thing you want to do is calculate moles. So you have 50 centimeters cubed of hydrochloric acid, but its concentration is in decimeters cubed. So you want to divide that 50 centimeters cubed by 1,000, right? And you're going to multiply it by 1, because the concentration is 1 mole per cubic decimeter, and so you're going to have 0.05 moles of HCl. You're going to do the exact same thing with your sodium hydroxide to see that there's also 0.05 moles of that. Next thing you want to do in step 3 is calculate your heat. Remember, this is going to be T equals MC delta T, and you don't have to remember this because it's in your data book. So 50 centimeters cubed plus 50 centimeters cubed equals 100 centimeters cubed total of solution, right? So that's all the stuff that you're going to have in your polystyrene beaker. Now, 1 gram of water is going to equal 1 centimeter cubed of water. So therefore, because we have 100 centimeters cubed, our mass is going to equal 100 grams. Now, your specific heat is going to equal 4.18 joules per gram per Kelvin. Your delta T is going to equal 23.5 minus 16.7, because the final temperature minus the initial. So you're going to have a 6.8 positive temperature change. And notice how, even though we're in degrees Celsius, a change in Celsius is still going to equal a change in Kelvin. And then lastly, you can get your Q equation by saying 100 times 4.18 times 6.8 equals 2,842.4 joules. Now we're going to plug this into our delta H equation, and we're going to have a negative Q per mole, because this is an exothermic reaction, because our heat increased. And so you're going to get 2,842.4 divided by 1,000, divided by 0.05. Remember, this divided by 1,000 comes from delta H is measured in kilojoules and Q is in joules. And so after you do that, you're going to divide it by your moles, which is going to be 0.05, because they're going to react evenly as according to mole ratios. And you're going to get negative 56.8 kilojoules per mole. That's going to be your answer to the question. So it is possible that you might see on your exam that you need to extrapolate data, or kind of create a line of best fit. So if you're given problem, such as a known volume of copper sulfate solution is added to a calorimeter and its temperature measured every 25 seconds. Excess zinc powder is added after 100 seconds and the temperature starts to rise until a maximum after which it falls approximately linearly with time. So you have a solution, you're going to add zinc to it, and it's going to react with this copper. And our temperature probe is kind of reading this, gradual change over time. But we know that's not going to be true, right? Because we have to assume that there's heat loss to the surroundings. And so we're going to take our maximum recorded temperature, right? And we're going to, create a line or create a graph with everything that follows after it. After that, you're going to use a calculator and you're going to calculate a line of best fit for this equation. And you're basically going to go all the way back to when the zinc was initially added to see what the maximum temperature could have was if there was no heat loss, right? So here, extrapolating this line, we're going to get 70 degrees Celsius. Now, enthalpy cycles are also something that you might see on your exam, and don't be too worried about them because they're pretty easy. Enthalpy cycles can be used to find the difference in enthalpy between two different compounds when given the delta H of the same compound. So, for example, if you wanted to see how, let's say that you didn't know what delta H was for the reaction of graphite, hydrogen gas, and oxygen to make C2H5OH or ethanol. So, but you do know that this reaction creates this, and this reaction can also create this, right? So, oh man, I apologize. So, notice how this is a negative value. Sorry. So, notice how this arrow goes in this direction. So, we want to get from this to this to figure out what this delta H equals. And it might be easier to represent it if I turn on the pen, clear all, and just say that we don't know what this is. We can say that this is X, right? And so this arrow is, we have an arrow going to here, and we want to get to here. Well, if this arrow is going this way, and we want it to go that way, that means we're going to have to negate our delta H2. And so, so if you add up the reaction pathways, right, because our reaction pathways are, you go from this to this, and so you have to add those two together, arrows going together to get this final product. You're going to have a negative 1646 kilojoules per mole plus a negative 1367 kilojoules per mole. Because remember, this value comes from this reaction proceeding in this direction, but we want it in the opposite direction. So if you see something like that and doesn't make sense, just know that if a reaction is going in it goes in one direction and it gives you like a negative value, it's going to become positive once you flip it in the other direction. And so once you do those calculations, you get negative 277 kilojoules per mole, which, if we turn off the pen, that's our answer. And so this is also called Hess's law, which states that the enthalpy of reaction is independent of the route taken. It's basically just saying that there's a conservation of energy across, time and space. So this, these components can get here in any sort of way, but however they get there, it will always overall be an exothermic reaction of 277 kilojoules per mole. Now, the next thing I'm going to talk about is bond enthalpy, right? So bond enthalpy is the energy needed to break 1 mole of bonds in the gaseous state into gaseous atoms averaged over a variety of similar compounds. Therefore, delta H calculated using bond enthalpies are only accurate for gaseous state reactions. This gaseous part is really important. If you're asked to define bond enthalpy, you will not get the point if you don't say gaseous. And if you're using bond enthalpy, you have to make sure that you're using bond enthalpy of gases or of any gases in the compound, right? So bond enthalpy, you have bonds breaking, which is endothermic, or a positive delta H. And you have bonds forming, which is exothermic, and a negative delta H. Call back to when I said that chemical energy is, needed to break bonds and is released when bonds are formed. So all your bond enthalpies are going to be found in section 12 of the data book. So if you're ever asked for bond enthalpy, go straight there. Now, your delta H of reaction using bond enthalpy is going to be the sum of all the enthalpies of your broken bonds minus the sum of all the enthalpies of your bonds formed, or i.e., the sum of all the enthalpies of your reactants minus the sum of all the enthalpies of your products. So here we can see we have ethene, which reacts with hydrogen gas to produce ethane. So our reactants have a total of 2,706 kilojoules per mole if you count up all the bond enthalpies in the data booklet. So you'd say, oh, there's a double bond here. You go to the carbon-carbon double bond, and they give you a kilojoules per mole value. And then same with carbon and hydrogen. Because your CC double bond is equal to 614 kilojoules per mole, your four times the carbon hydrogen bonds are going to be 4 times 414, and your hydrogen is going to be 436 because you have to account for this one as well. Your products, meanwhile, are going to be 2,830 kilojoules per mole by doing a very similar set of steps. So we're going to take our bonds broken, our reactants, minus our products, and we're going to see that our bond enthalpy for this reaction is negative 124 kilojoules per mole. Now, we're getting into some HL stuff. You have standard enthalpy changes of formation, delta H formation theta, and combustion, delta H C theta. Now, standard enthalpy change of formation is the enthalpy change when 1 mole of a compound is formed from its elements in standard states at standard conditions, or 100 kPa and 298 Kelvin. Standard enthalpy of combustion, enthalpy change of combustion, on the other hand, is the enthalpy change when 1 mole of a substance is completely combusted in oxygen under standard conditions. I cannot express how important it is to understand that both of these standard enthalpy changes are going to be 1 mole, right? I have messed up on tests and other practice exams where, it'll give me standard enthalpy of formation and combustion. I'm like, oh yeah, that's an easy problem. I write out the reaction, and I always mess up because I end up balancing the equation. It is 1 mole. If you have to balance an equation and then find the standard enthalpy change of it, don't worry about having fractions as long as your formation is 1 mole or your 1 mole of a substance is combusted, right? So don't worry. So always remember 1 mole for standard enthalpy changes of formation and combustion. Now, these are going to be in your data book sections 13 and 14 respectively. And your delta H of reaction is going for formation is going can either or sorry, excuse me. If it's formation, the delta H of the reaction is going to be the sum of all your standard delta H formation products minus the sum of all your delta H formation of reactants. Now notice how this is flipped from the what do you call it? The bond enthalpy equation, right? So make sure you notice that. And then your delta H of reaction is also going to be flipped from this, right? If it's combustion, it's going to be reactants minus products. If it's formation, it's products minus reactants. So your standard enthalpy changes of formation are going to be more accurate than your bond enthalpies because these bond enthalpies can be affected by other characteristics, like intermolecular forces, while these standard enthalpy changes of formation and combustion are going to be like averages of like actual experimental values over long periods of time for these specific compounds. Now, enthalpy change of an element in its standard state is always 0, right? So if you get something in standard state, like carbon as soot or something like that, or graphite, just know its enthalpy change is 0 because there is no energy required to make something that exists naturally. Oh, that's gonna be awful writing. Hold on, I apologize in advance, but I want to get this out. If you can read this, you are a trooper. All right. Now, delta H of combustion, something you need to know for this is that it's always exothermic, except for nitrogen dinitrogen gas. Its bonds are way too strong for it to be exothermic. I don't think you'll see that on your exam, but just in case, know that delta H of combustion is always exothermic, except for N2. Now, okay, I want to make sure I didn't miss anything. So your Born-Haber cycles are energy cycles for the formation of ionic compounds. So it's important to think about in steps, and these consist of experimental data. So lattice enthalpy is the enthalpy change that occurs when 1 mole of a solid ionic compound is separated into gaseous ions under standard conditions. Gaseous ions. Remember your terminology because it can very easily mess you up. Now, smaller ion plus greater charge equals a higher lattice enthalpy, right? So let's take, for example, NaCl. And the lattice enthalpy of NaCl is going to be NaCl solid to make Na positive sodium gas and negative chlorine gas. So your enthalpy of atomization is something else you need to know for the Bohr-Haber cycle. And it's the enthalpy of atomization, which is the standard enthalpy change when 1 mole of gaseous atoms is formed from an element in its standard state under standard conditions. For example, enthalpy of atomization would be taking chlorine gas, diatomic chlorine gas, and making 1 mole of just chlorine gas. So this is what a Bohr-Haber cycle is going to look like, and I'm going to try and walk you through it, right? So typically in a Bohr-Haber cycle, we're trying to figure out what the lattice enthalpy of a specific compound is. And since we know that lattice enthalpy is when 1 mole of a solid ionic compound is separated into gaseous ions under standard conditions, we're going to start with standard conditions, elements in their standard conditions, and we're going to kind of work our way up to getting our gaseous ions. So we're going to start here, at least for this one, and we're going to have, so we have, you see, your solid sodium chloride at the bottom, right? We have a negative 411 delta enthalpy of formation difference from here to here. So, keep that in mind for later. We're going to start with what it gives us, sodium solid, and 1/2 chlorine gas, right? So we already have the enthalpy. We have our chlorine gas and our sodium in the standard states. Now we're gonna have first atomized sodium, so that's gonna be a plus 107 kilojoules per mole. And it should give you these values. I do not believe in the data booklet. It should give you these values per problem. So you're gonna see that as we go up, we're gonna change our sodium solid into sodium gas, and then we need to atomize chlorine gas. And so we're going to take the bond enthalpy of chlorine, and we're going to multiply by 1/2 because we only have 1/2 of diatomic chlorine. Because your values are going to coincide with your moles. So now we're going to have sodium and chlorine gas. To ionize sodium, we're going to have to add 496 kilojoules per mole. So we're going to go from solid sodium to positive sodium plus an electron. And then we're actually going to release energy as we give chlorine another electron through electron affinity. So it's going to take that electron. Now we have our solid sodium, or not our solid sodium, our gaseous ions, right? On the next step, we'll be getting them to their solid ionic compound. So now that we have all these values, we're going to add them up together to get our lattice enthalpy. So if you look at the problem down here, we're going to have 107 plus 496. Obviously, this in order. But they can add the delta H of atomization for sodium, the delta H of ionization for sodium, the delta H of atomization for chlorine, and then they're going to add the electron affinity for chlorine. And then finally, as you can see, we have standard states to the ionic compound. And so because this arrow is going down, we need to go up to get here. Notice how this arrow is blue and all the other ones are red. We're going to flip it or negate it so that our negative 411 kilojoules per mole becomes a positive 411 kilojoules per mole, which is why we subtract it here. And that's going to give us our final answer of 786 kilojoules per mole. I hope that helped, but if it didn't help, I recommend looking at some more examples. Now the next thing we need to talk about is energy from fuels. Combustion reactions, because they are almost always exothermic, allow us to obtain energy from chemicals. So complete combustion of hydrocarbons, which are carbons with hydrogen, so it can't just be any carbon compound, produces carbon dioxide and water. Incomplete combustion of hydrocarbons produces carbon monoxide and carbon. Longer chains of hydrocarbons are more likely to combust incompletely. Incomplete combustion is bad because carbon monoxide binds to hemoglobin. That's supposed to be capital. I apologize, I didn't even see that. In blood and prevents transfer of oxygen And carbon is bad because it's particulates like soot or poisonous. So some environmental aspect of the gene that you need to know is that catalytic converters in cars can convert carbon monoxide to carbon dioxide. And then you're going to get here in this table, we're going to have 4 different types of energies. We're going to have hydrogen gas, methane, I believe this is octane, and this is going to be methanol. And so you can see that the energy released per unit of mass. So, hydrogen is going to have the most energy released per kilojoules per gram. So in mass, it's going to be the most effective. But in terms of volume, it's going to be the least effective, right? But because there are no carbons in hydrogen, you're going to want to know that's the cleanest of all your fuels. And then, just to try and re-explain this, because I'm thinking about it and I'm worried that it might not make sense. Your energy released per unit of mass is the energy released by, 1 gram, right? So if you have 1 gram of dihydrogen, that's going to be a lot because 1 mole of hydrogen is only 1.01 grams. Whereas if you have 1 gram of methane, that's not going to be a full mole of methane. It's not going to be a full mole of octane or anything else, right? Which is why hydrogen is going to have the most. But if you look at energy release per unit in volume, all moles have the same amount of volume, or occupy the same amount of volume. So 22.7 decimeters cubed, right? Whereas this was hindered by, you don't have as many moles of these as you have moles of hydrogen. These, now they're on an equal playing field. You can see that octane is going to be the most efficient fuel source per volume. Some fossil fuels that you're going to need to know are crude oil, coal, and petrol. And petrol can be separated from crude oil via fractional distillation. Most energy comes from the sun, allowing plants to convert light into energy to chemical energy through photosynthesis. So the chemical reaction for photosynthesis is going to be 6 carbon dioxide plus 6 water to make glucose and oxygen. So some advantages of sustainable fuels, not sustainable fuels, biofuels like ethanol, which is C2H5OH, is that they are cheap and readily available, and a disadvantage is that they use land which can be used for other purposes such as growing food. I wouldn't memorize most of these, but I picked like 2 from each category and said, okay, I want those. Now, here are the advantages and disadvantages of different types of fuels, like fossil fuels from coal and petroleum to just natural gas. And feel free to pause and look at this table and write anything down. I'd recommend same with the biofuels table, looking at 2 that you think are important and identifying them. Now, the next thing that we're going to talk about are hydrogen or fuel cells, which are going to be separated into hydrogen fuel cells and methanol fuel cells. So a hydrogen fuel cell is going to look like this. We're going to have a hydrogen gas, which is going to react with oxygen gas to make water. 1 mole of water, delta H, because it's a standard delta H formation. So the transfer electron, which is why you have that 1/2 oxygen. So the transfer of electrons allows easy transfer of chemical to electrical energy, and reactants must be separate, as in different electrons. This is true of all fuel cells. So all fuel cells, it's just to an extent, are the transfer of electrons. And we can harness that chemical energy to become chemical energy to become electrical energy. So the hydrogen fuel cell occurs through the redox reaction of hydrogen and I believe that's what we go to, or H2, sorry, and oxygen gas, where hydrogen is going to donate its electrons to oxygen to become oxidized. Now this can occur in alkaline or acidic electrolytes. Its reactants are going to have to be continuously supplied, and this is what a full redox reaction for this equation would look like, where you balance them out and you have to figure out, okay, what's gaining electrons, what's losing electrons, because these fuel cells are transferable electrons. And if this looks a little daunting to you, don't worry. There's going to be an R3 video that's going to explain half reactions more in detail and redox reactions as a whole. A disadvantage of hydrogen fuel cells is that hydrogen itself is almost never found in nature and requires electricity to produce. So you're putting in electricity to get electricity out, which is just not that helpful. So methanol fuel cells, you don't have to know as much about. You need to know that it has to be a stable liquid at normal conditions. Methanol has a high energy density. The fuel is oxidized in acidic conditions with catalyst. So unlike hydrogen fuel cells that can be alkaline or acidic electrolytes, it has to be in acidic conditions with the catalyst. And methanol fuel cells are going to produce water and carbon dioxide. And here you can see the methanol half reactions for a methanol fuel cell. So you're going to have methanol plus water. It's going to make carbon dioxide and 6 electrons and 6 hydrogen. So here you can have your methanol. It's going to break down, and it's going to be, I believe, oil rig, oxidized. And then you're going to have your oxygen, which is going to undergo a process and be reduced into water. And then you're going to join these two together, and that's going to give you this full equation. So, as a general tip for half reactions, you always want to make sure that your electrons cancel out on both sides. And I know this looks daunting, but I just recommend some practice with like basic half reactions and basic redox reactions. Kind of ground your feet, because once you ground your feet, it becomes a lot easier. So now we're going to talk on HL topic, entropy. Entropy, or represented by S in joules per mole per Kelvin, is the distribution of energy among particles, or you can call it chaos. Reactions are going to be spontaneous if they increase total entropy. Increases in entropy come from mixing different types of particles, changing states, and increases as you go from solid, liquid to a gas. It makes sense of that, right? Because solids move a lot less than liquids, and liquids move a lot less than gases. Solids are compact, they're held together, while liquids and gases are not. So these are going to have a lot more movement, and therefore the distribution of energy is going to be larger. Now, entropy can also be increased by increased movement of particles by applying heat, or, most importantly, increasing the number of gaseous particles that you have. So here's a chart I made for that needs to come later. Delta S is going to equal the sum of your products minus the sum of your products minus some of your reactants, and these data values are going to be in section 13 of the data book. And before I want to go on, I want to say I apologize. I should have seen that this is not supposed to go here. I got a little ahead of myself, but with reference to reactions are spontaneous if they increase total entropy, right? So here's a way you can tell that reactions are spontaneous. If they decrease total enthalpy, right? So they are exothermic, making the products stable, and we're making the reactants more stable. And it increases entropy. It is always going to be spontaneous. If it increases entropy and it increases enthalpy, it's going to be high, but not impossible, but not always, right? If it decreases both, it's going to be low, and if it increases enthalpy and decreases entropy, it's going to be never, right? So, the universe wants entropy to occur. It leans towards chaos. So Gibbs free energy, or G in kilojoules per mole, is the total entropy change of a system. Reactions are spontaneous when standard Gibbs energy is negative, moving from less stable to more stable. So it's going to just Gibbs free energy. Think of it basically as, can a reaction be spontaneous? So the equation for the change in Gibbs energy is going to be delta G equals delta H minus temperature times delta S. Now, I want you to think back to the chart that we drew, always high, never low, right? So if we draw that chart, if we draw a chart really poorly, I'm going to draw it down here. I hope you can tell I did not take IB art, but if we have delta S on the y-axis and delta H on the x-axis, well, if Gibbs free energy is basically, can it be spontaneous? And spontaneous reactions occur always high, always high, never low, right? Which is kind of the monogram I like to think about, or not monogram, but the phrase always high, never low goes in a circle. Well, if delta S is positive and delta H is negative, well, if delta H is negative and you have a minus, you know, negative minus another number, that's going to be a greater negative. And reactions are spontaneous when standard Gibbs energy is negative. So if you're a math kid, you might be able to think about that in a better way and see how, okay, well, if delta H is positive, that means that delta S has to be really big in order to make delta G negative, which is why it's high, but not, always. And the same goes for the low and never. Then Gibbs free energy of formation is the free energy change when 1 mole of a compound is formed from its elements under standard conditions. Elements in standard state have a delta G of equal to 0. There's no energy required to make something that naturally occurs. And the delta G of a reaction can also be represented by the delta G of your products minus the delta G of your reactants. Delta G of formation of your products minus the sum of your delta G of reactants. So Kc is going to be known as the equilibrium constant. It's going to equal products to the power of their coefficients minus the reactant, or divided by the reactants to their coefficients. So if you had a chemical equation, you take your concentration of your products on the right side, and each to their own coefficient. And maybe a better way we think about this is if you have product C and D, right? C is going to be raised to its exponent, or its coefficient. Let's say its coefficient is x, and D is going to be raised to its coefficient, which is going to be y. And then you can divide it by the products, the concentration of your A, and the concentration of your B. And then these are going to, oops, that's a disgusting B. I wish I could erase that. If I can, I don't know how. I apologize. But you're going to raise these to their own things. We're going to say U or Z, and we're going to put U as W, right? So you're going to have each product, the concentration of each product, to the power of its coefficient, and multiplied by the other, and then divide by the reactants. That makes a little bit more sense. If delta G is negative, the reaction shifts to the right, or K is greater than 1. And think about it, right? If delta G is negative, then a reaction is spontaneous, meaning that you're going to create a lot of products. And so K is going to be greater than 1 because you created a lot of products, and your products are going to be greater than your reactants. That's why I should have defined equilibrium, but equilibrium comes in R2, R3. Apologize. But it's basically just when a chemical equation meets a balance and it has equal back and forth reactions. But all you need to know in relation to Gibbs free energy is that if delta G is negative, the reaction shifts to the right. If delta G is positive, the reaction is going to shift to the left because it's not spontaneous. And so your reactants are going to be greater number than your products. And if delta G equals 0, the reaction is at equilibrium. So another equation that you might see is delta G, or standard delta G equals negative Ratlink, which is what you might want to call it if you need to remember it. And so you're going to have your ideal gas constant, R, multiplied by temperature in Kelvin, and then the natural log of your equilibrium constant. And for that, that's actually it. I don't know at the time of recording this if I was able to make it shorter than last time, because I had this an actually short one, and it actually was short. But thank you so much for watching and making it to the end. Hopefully you feel a little refreshed on this content, and you're ready to tackle your exams. If you like this or if you found it helpful, feel free to like, share, and subscribe, but only if you feel that you want to help me out and that I help you out. And with that, I bid you farewell. Thank you for watching. Bye-bye.